progress like there's no tomorrow.
Welcome everyone to the second block of the lecture number 6 on building of yield curve. Today we will discuss yield curve construction, of course. It will be a very practical block where I will show you how to develop an algorithm for building of a curve. We will also perform the curve calibration, let's say, on slides. And then very important 2 elements where we will analyze Python code on how to build a yield curve given market instruments, particularly swaps. And then we also will discuss the impact of different interpolations on our hedging. So it will be a very practical block, and I hope you will learn a lot from it. Let us now define the iteration routine for construction of a yield curve. So we already described, we have a vector of n instruments, so we have n PVs, and we would like to find out those zero coupon bonds or spine points, given interpolation that the PV will be equal to 0. So this is the, you can say PV, which is equal to the market instrument minus quote. So this is how we define PVs. Okay, so what we have to do, we perform the iteration as we have done it for implied volatility. However, this time we have to do it for the multi-dimensional case. But it's not so much actually different than single dimension, except that we have to make sure that we are dealing in the proper places with vectors and matrices. So iteration is as follows. So the PV, the new vector of spine points plus delta df. So this delta df is the delta of adjustments that we have to perform into spine points. That will be equal to the PV at the previous iteration. And then we have a sensitivity of our PV with respect to those spine points. So we have to calculate this derivative, partial derivative, and times dft. So you can see this expression is just a Taylor expansion from PV df, and then we have a delta df. This derivative here, so we can also associate, we can easily see that this is, we have a function with a vector of PVs. We calculate each of these individual PVs with respect to spine point, those derivatives. That's simply called Jacobian. So this is Jacobian we have to calculate for this whole vector of PVs. So this is simplified notation, and of course we have also an error, which is order of a delta df squared. So this is a classical result from Newton-Raphson that we have discussed already before. Okay, so this is simple iteration process, but this is not finished yet. First, let's write it down in the matrix notation, because at the end we have to implement this optimization in Python. So we have this, we have a vector of n instruments that we want to use to build up our yield curve. And this will be equal to the previous value of the previous iteration with respect to those spine points. We have a Jacobian, and we multiply this Jacobian with a df once. So we look at the differences between, so this is this df here, and the same vector will be used here. This is for each of those individual rows. So essentially, if you see, if each of these rows has to be multiplied with this column. So essentially, we have a summation of the row of Jacobian matrix with a column here of a df, of delta df i's. That's it. So we can write it actually down for each individual I that we have now. For each individual PV, we have, as we had, so this is the next step, next iteration is equal to the previous iteration, and then we have a summation of each individual derivatives, so of all the PV i's, because this is ith instruments, so which is here, derivative to dfj, so j going from 1 to n, and then we multiply with this dfj, so this is for each individual j. Okay, next step is to set this next iteration. So for each individual instrument, we set this value to 0. This means that we are enforcing this condition that the next iteration has to be equal to 0. And that's actually the target of our optimization routine. So once we define it, fix it at 0, then we have the following steps. So we have PVI, df, then we have this summation, and this is the term what we have for the error. And okay, what we see is that because we force it that this term has to be equal to 0, then what we can do, we can find out what is the next. So what we are interested in, essentially, we're interested in how we have to adjust our vector of df's, so the adjustments for each individual spine points, such that this error will, so that we get our convergence. Because this is unknown. This is exactly how in next iteration we always defined in terms of a previous the vector of a dfi's. So we need to, each iteration, we have to find out what is the vector of dfi's such that we can perform the next iteration. So from here, we can see that we take this on the left-hand side, it's with a minus term, and then we have here Jacobian dfi. So then we have to, both sides of equation, we have to multiply with the inverse of Jacobian, and this is the term matrix notation we have. So delta df is equal to minus Jacobian, the inverse of Jacobian, evaluated at df, and then we have a PV df. So this is actually coming from the inverse, it comes from this term, which was put on the other side of the equation. So this is actually, this determines our delta df, because we enforce this expression to be 0. That gave us this optimal, or the next iteration, the improvement, the adjustment for the delta df. And now what we can do, we can, using this expression, we can plug it in back to the to adjustments here for the df's. So you can see we have a df new one is equal to the old df minus Jacobian that we have with as a function of previous, as a function of df at the previous step, and then we have this vector of PVs evaluated previous vector of spine points. So this is the iteration that we have to perform for the evaluation for finding optimal spine points to build a matrix. And this is very similar to what we have done here. Let's go back. You see, this is very similar to what we have done here for implied Black-Scholes volatility. So you see that we had this iteration of sigma n plus 1 equals to sigma n. And then we have 1 over derivative. So this is this inverse of a Jacobian. And then we have our target function evaluated at the previous sigma n. So it's a PV. Actually, this can be considered our PV that we have in the representation. So this is exactly the same step, except now we are dealing with matrices and vectors. That makes it slightly more difficult. Okay, so also important point is that if you look here, we have defined everything, that we have those vector of discount factors. So okay, now is the question how to choose those discount factors, where they are actually, how we specify the spine points on the curve. Because essentially we have, this is our input, we have to specify what are the pairs, TIs, and also discount factors that we are going to optimize. So we always have to specify the grid before we find this optimal zero coupon bonds, we have to specify the grid of points, TIs, and also indicate where actually the grid, what are the instruments used to build the curve. So if we take, for example, this is a nice example. So you will see how to approach it, how to look at the instrument, which has multiple payments, how to map that instrument to a spine point. To give you an example, so we have two instruments. So objective is to build a swap, a yield curve for two interest rate swaps. We have a 2-year swap and 5-year swap. So this 2-year swap will have payment in a year and also 2 years from now. And we have a 5-year swap. Okay, so this 2-year swap and 5-year swap, they have two instruments, but each of them, this one has two payments, and this one has 5 payments. So if you write down this PVs, so 2-year and 5-year, and the value of a swap, I call it just a function psi, here will be depending on 2 zero bonds at 1 year and in 2 years. For the second swap, we have 5 swaps. Sorry, 5 zero coupon bonds, 5 spine points. So we have a little bit of problem here because, as you can see, we have only 2 equations. We have used 2 instruments to build the curve. However, we have a number of unknowns is 5. So that's a problematic, because if you look now, for example, at Jacobian, it's not a square metric, so we cannot really invert this matrix. So this means that this system is underdetermined. We don't have enough information to build a yield curve, essentially. So we cannot actually, if we approach this problem from this perspective, where each payment of a swap would be a spine point, this means that we cannot do it because we have not enough information. Of course, now we could say, okay, let's introduce extra market instruments. For example, instruments for zero coupon bonds 3, 4, and 5, and that would give us solution. Of course, if we create extra equations, so we add extra 3 equations, then this problem is well defined when well posed, and we can find this inverse of a Jacobian and we can iterate. However, you see that who knows that those instruments, let's say 3-year, 4-year, and 5-year, those are actually available in the market and they are liquid. That's very unclear. So the objective, so this is not the way to do it. So this is clearly states that this is a problem for building of a yield curve. Alternative to it, and actually this is what is a common market practice, is to only look at the payments, the final payments of a swap. So for example, if I have 2-year swap, I have only one spine point at 2 years. If I have 5-year swap, I'm only looking at the spine point at 5-year. In this way, if we do it this way, we have only 2 equations and 2 unknowns. Then the problem is well defined. Of course, at this point you can ask, okay, what about the points in between? And the answer is points in between, that there are payment dates, but they are not used as spine points. Those will be determined by interpolation. So you can say, you can already see that this interpolation is extremely important because this interpolation will determine what is happening in between your last payment date. So between the end of this swap. So indeed, so this is the 2 points I want to mention. We can add more instruments to fix this problem, but this is not really advised to do it. And the solution, and actually something that is very, very important, solution that we always consider only the last payment, those will be our spine points. So you see, if you have one instrument, you can also with one instrument build a curve, because this yield curve would have only one spine point, and everything else will be interpolated and extrapolated. And so extrapolation is also very important. If you have 2, you have only 2 spine points, and everything is still well defined. So number of instruments will equal to the number of spine points. This is the most important message from this slide. And this is how this operation can be built. Otherwise, imagine a swap, 30-year swap with a frequency of 1 day. Imagine that, how huge problem would be then for determining all those spine points. That would be just impossible to do. So this is, I think, informative slide, and I hope that it's clear now how to look at those instruments and how to link those instruments to spine points. Although you never do it in practice, I would like to show you how to construct a yield curve essentially on paper. In this example, we will look at a construction of a yield curve using 2 instruments. The one will be forward rate agreement, and the second will be a swap, a simple swap. So we will go step by step how to compute essentially spine points, how to construct those iterations in order to find the optimal solution. Next block, we will discuss, though actually in a Python implementation, how to do it numerically. So you hardly ever do it by hand, actually never. However, this is good for illustration purposes. You can also then check your code whether if you follow the same strategy, you will get the same solution. So, okay, so first, what we do, we define the forward rate agreement. This contract was already discussed in this course, so please revisit if you're not familiar with. We have some zero coupon bond here, and we have LIBOR dependence. So this is LIBOR rate, also defined in terms of zero coupon bonds. So the settlement here, we will simplify it slightly because it's not so important. This is more like showing you the process of constructing of this yield curve. So we choose some simplified dates. So we have a settlement date for this FRA agreement, which is a 2 times T0. And also we make the first payment to be exactly equal to 1 year from today. Then our FRA is simply LIBOR rate minus strike. And then we have the discounting with a LIBOR rate. So if you look at this PV, so the PV that we are going to use as a target in our optimization, this will be defined as the difference between the FRA as the definition of a contract against the quote in the market. This is very important also to keep in mind that if you build a yield curve, typically those quotes, quote in the market, those will be typically zero, because those instruments that we are going to use to price in order to construct a yield curve, typically those will be par instruments. Par instruments, we already have this discussed earlier in this course, those are the instruments that it costs nothing to enter. And those are typically the most liquid ones. This is why for most of the cases, this QI or Q1 in this case will be equal to zero. However, just to keep it generic, and also in the code, you can also change this value of these quotes just to see how this play out, what is the impact of it. But essentially, also you can see from the numerical perspective, if you look at this derivative of Q1, actually it's zero, so it's not so relevant. It's just a constant shifting. However, in a target function, this is relevant, right? So this is important. Okay, so if we substitute now the definition of a LIBOR rate, so LIBOR rate is the rate, so we have a accruing period, and we have a ratio of the difference of two zero-coupon bonds divided by the later one, so the definition of a LIBOR rate, then our PV1 can be expressed as follows. So everything is, actually this is time T1, T2, but if we substitute those times T0 and Tm, actually T0 and 1, because this is the case we consider here, then we can express this PV1 to be equal to 1 over df1 minus 1, and then we have the strike 1, and then we have here the almost the same expression for the 1 plus, and then we have this LIBOR here, which is, and then this is equivalent expression, minus 1. So we can also simplify it further, because if we reorder some of those terms, we can reorder those df1s here, and then the simplified expression will be 1 minus 1 plus k1 times df1 minus q1. So you see this expression essentially is purely a function of a df1. So that's one unknown, one equation. So from here we can already find out what the df1 should be in this case actually. However, we also have a second set. We have a second instrument. We have a swap. In swap, we also have here two payment dates. So we have 1 and 2. So those are the first one, number 1, the first year, and then we have a second year. And if we collect all those terms, if we do the substitution here, because this is summation of those, this is which one zero-coupon bond will be summing up. So then we have df1 minus df2. We have k2 minus this tau accrual, which we set to 1, because it's t1 and t2, the difference is just to 1 year. And then we multiply, with df2, so this is the second payment, because then we only do it at n. So this is this term, and then we subtract q2 equal to 0. So this is our second set of equations, second equation in our set. So this is our matrix. So we have a vector, it's a vector of two equations, and then we can calculate from here the Jacobian. So we do Jacobian sensitivity with respect to the first discount factor and the second one, and we do it for each of those equations. Then, of course, in the first equation is not sensitive at all to our df2. So this is just we only sensitivity to the first zero-coupon bonds. This will be 0. And then here for the second one, I think this should be done. There is a mistake. This should be 1 actually here. Yeah. This 1, and then we have a minus 1 plus k2. So this is important. And then if we do the inverse of this matrix, then we have just this the following expression. This is determinant, and then we have this lower diagonal matrix. So also important to notice that if you have swaps that are only swaps are used to build your curve, then essentially we always end up with a lower triangular matrix, because the first swap will be the first spine point, second swap will be the second spine point, and so on. So then we always end up with a lower triangular matrix, and then the inversion will be also can be done much more efficiently. And already as I mentioned that those strikes, Q1 and Q2, typically they're chosen such that the value of those contracts is equal to 0. So this is something to keep in mind. However, not always. Yeah, you can always choose instruments which are not priced at par. that could also be incorporated in this methodology. So this methodology is insensitive whether we have par or not par contracts. Now is the time to collect all the knowledge we have gained in this lecture and also previous lectures on building of a curve and how important it is. And we will construct our curve ourselves. So for that reason, I have downloaded some data from a US Department of the Treasury. So this is the link that you can download yourself. So you see, let's analyze first the data that we have. So those are the dates at which the curve or the rates that were available in the market are stored. And then we have particular settings, the maturities of the underlying contracts. So those first points, 1 month, 2 months, and so on, those are typically the LIBOR rates or some cash instruments, maybe. Those are implied the LIBOR rates. And here, when we have 1 year, 2 year, 3 year, and so on, those are the swaps that we are going to use today. So basically, the objective here is to take market data from the US Department of Treasury, take those quotes as those are here. Those are the par quotes. So this means that for this particular strike, the value of a swap with 3 years of maturity, it will be equal to 0. So we take those quotes and we try to build a yield curve for those quotes. And then we will check whether the yield curve actually priced all those instruments back to par. Let's take a look at the codes. Okay, so this function is a little bit more complicated than we have seen before. So it requires some attention to really digest what is happening here and why it actually works. So first, we go line by line. So first, we specify here a tolerance, the convergence tolerance. So we have this multidimensional Newton-Raphson. We have to make choose some stopping criteria for the optimization algorithm. So here we have a quite high requirement. So this means 10 to minus 15. Then only at that level, we will stop the iterating in Newton-Raphson. You will see actually that it 10 to minus 15, this convergence in this kind of building of a curve, it only requires few iterations to find a proper, or let's say, priced back to par curve. We specify some initial spine points. So those are I just chose everywhere to be 1%. So you see it's 1% for all of the instruments. Here, we also, like I already mentioned before, yield curve is very important for the building of a yield curve that we choose interpolation routine. So here I have specified linear interpolation. This is just a method which is essentially interpolating linearly in a given vector of Ti's and Ri's. So we see this linear interpolation here. We have a vector of Ti's and Ri's, and here is just a lambda expression which will perform linear interpolation. So for every time, we'll interpolate linearly between those points, between those spine points. So we are essentially interpolating on a log of zero coupon bonds. You can think like this. Log actually divided by time. This is also important because this is what we do here. Okay, so this is linear interpolation. Later, we also discuss how the hedging can be done once we switch interpolations and how this will have impact on our deltas, on our sensitivities. Okay, here are the quotes that I have taken from the website. So you can see here we have everything has to be divided by 100 because that quotes were given in percent. So we have everything is divided by 100. Yes, because even this is the latest, I think, 30 year. So this is the matrix, or vector for maturities. We have 30-year swap, which pays 2.3%. So we have to scale it down to divided by 100. What I'm doing next, I'm dividing for each of those swaps because we have to evaluate each of those swap instruments on a whole vector of the spine points, right? So actually, whole vector of spine points, a function of a zero coupon bond. So you see that for zero coupon bond, which is an input, I'm evaluating a swap. Let's take a look what swap function does. So swap function has some configurations. It's a payer or receiver. We have a notional, which is irrelevant for our calibration purposes. We have a strike, so fixed rate for a payer or receiver. We have a time t, which is actually, in this case, once we build a curve, it's only T0 because we build it from today's perspective. However, this, let's say, flexibility of choosing this today's date, it will be important later in a few lectures from now when we will be talking about XVA. Then actually this T argument is important because then we have to trace our paths and we know exactly where we are in time to know which coupons we have to pay and which coupons have been paid. Then we have a beginning of a swap, so it's Ti, and then we have end of the swap, and N indicates the frequency, so how many payments will happen between time Ti and time Tm. So this is just a swap. You see, essentially here we just define, we sum zero coupon bonds at the first payment date, the last payment date, and we divide it by the annuity, which we also calculate from this zero coupon bond. Important part here is that we have this zero coupon bond, which is the input for this function. So whatever happens, how this function is constructed, whenever it's called in this as an input, we just evaluate swaps for this zero coupon bond. So here what I'm doing, I'm defining a swap to be a lambda function of that zero coupon bond. So whatever zero coupon bond is chosen, then we perform evaluation of a swap for that zero coupon bond. And we have to do it for every individual swap, because essentially here nicely in Python, we can define those as just a lambda expressions. Normally, the concept of a yield curve, it typically in an object-oriented language, you would choose it to be an object that you can pass on and you can perform this calibration on the object. Here, I did it slightly differently, just to also for the purpose of illustration, to show you how exactly it works. So we have, you see, 150 lines of code, and we can actually do the whole yield construction. Normally in a production environment, if you have a big library, those will be thousands of lines of code. But this will facilitate the real understanding what happens. So we defined now 8 swaps. You see that for each of those swaps, I'm taking different swap rate from this vector, and I'm also taking different maturity. So this maturity is also taken from this maturity vector. Okay, so here I'm building instruments. So we have array of 8 swaps, and each of those swaps is a lambda expression, which depends on the zero coupon bonds. Objective here, find the zero coupon bond function, find this zero coupon bond 0t, such that all those instruments will be pricing back to par. And of course, this zero coupon bond function, it's a function of spine points and time. So those are the kind of level of abstraction we have here. Okay, so here, what we do, this is the key, most important part, where we do yield curve construction. Yield curve returns our spine points. So how this works? So we have a yield curve where we have instruments. So this is array of those swaps. We have a array of maturities, this vector here. We have a R0, which is the initial guess for our spine points. We have a method which tells us how to interpolate. So this is this method, linear interpolation. And we also have tolerance. Okay, let's take a look now from the yield curve. In a yield curve, what we do first, we do a deep copy of our initial. This is kind of important because otherwise those arguments are passed by reference, and then we will be modifying our initial guess. So we just make an initial to be copied, and then we essentially optimize, and then we perform actually the multi-dimensional Newton-Raphson algorithm on this deep copy. So this R0 will be always R0, even if we get out from this scope. Otherwise, if we would modify our R0 and we construct yield curve again, then this initial will be already something else than we expect to see. Maybe it will actually converge better. We will get better convergence because that will be closer guess. But the intention is that we always start with some initial that fix ourselves. Okay, a multivariate Raphson, Newton-Raphson. So okay, first we specify error. We choose 10 to 10, so it's a huge error. Now we do a while loop. So once we will repeat this loop until error is bigger than tolerance. So tolerance is 10 to minus 15. Until error is bigger than the tolerance, you keep iterating. So of course, you see that's a huge difference with 10 to minus 15, 10 to plus 10. So then it's quite some challenge for this optimization. But you will see this convergence will be very fast. Okay, what we do next? Of course, we have to keep track of the indices. So actually this is the index because I want to print them. You see that I'm having here an index, and I'm going to be showing you at each point what is the error. And error here is defined as the norm for the difference between our quotes and our values from the yield curve. Okay, evaluate instruments. So first we have to get those values. Evaluate instruments has a time, so 2 inputs, okay, actually 4 inputs. TI, so those are the spine points. RI are the times for spine points. RI are the spine points. Instrument is the vector of our swaps. And we also have method, and method is the linear interpolation. So let's go to this evaluate instrument. And what we do here, first we construct a yield curve given TIs and RIs. So those are the spine points. And we also have the method, which will basically construct this yield curve so that for every time we can have a zero coupon bond. And now what we do, once we have this zero coupon bond curve, we can evaluate each, so you see that I'm taking each swap. So each swap will be evaluated as the function of zero coupon bond. So it's a really nice, here you see in Python, you can really express it very nicely. So we iterate over all the instruments, and for each of these instruments, so here instrument I, we evaluate it as a function of a zero coupon bond p temp, which is defined in terms of times and spine points and interpolation method. So this is handy because we defined our swaps, you see, as the lambda expression of a zero coupon bond, and zero coupon bond is a lambda expression itself. So we have a lambdas of lambdas, you can think like that. So we change here our zero coupon bond, and then we evaluate our instruments. Okay, so evaluation of it. So we evaluated our trades, our contracts that we have in our vector. Then for this evaluated values, we will use those later once we talk about the Jacobian. But okay, so we have a values for our, let's say, current state of a spine point. Then the next step will be to calculate a Jacobian, which is the sensitivity of each individual PV, so our swaps, with respect to all the points that our spine points. So here we see that we have a Jacobian, which is calculated here. And we have we don't do it analytically. Jacobian calculation we just perform numerically. This means we perform some kind of, you can say, shocking of the curve of the spine points. So okay, so first we have a Jacobian we define as empty matrix. We calculate instruments for given all the points. So this is the same function we have done here. So in this evaluate instrument, we construct zero coupon bond curve and then evaluate all the swaps. Okay, once we do this, what we do, we make a copy of our RIs, of our spine points. So again, deep copy, make sure that actually you're not keeping the same spine points, because otherwise it will be a problem that if you are shocking something, maybe it's unshocked. So you have to make sure that you always have a copy of those instruments, of those spine points. And then what we do next is that so we perform iteration. So for every spine point, we will evaluate our instruments and we will store the results. So you see that basically here, we will have the output of this evaluate instrument is a vector, because we have a vector of instruments. So we will shock each individual spine point, and for each individual spine point shock, we will evaluate all the swaps. So this will be essentially every row. So every swap will be shocked for all the spine points. And then we have to do it again. So first, so we see that here is for the so we evaluate it once. We have to do it again for the shocked spine points. And what we do, so this is up shock, and then what we do, we will have a dv. So derivative will be a difference. So it's we do find a difference here. We do value after the shock up divided by the value without the shock. So this value. And we divide by epsilon, and epsilon is our case is the shock size, and this is what we do here. Should we do it? Yeah. So it's we do it for every column. Yeah, every column we perform this calculation. So this means that for every so for every spine point, we will have a vector of all the instruments. So this means in a Jacobian, every column will be evaluated. So Ri represents number of columns. Yes. Mm-hmm. Okay, and then we construct this Jacobian matrix. So you see this function is also very nice and very tight, because we just calculate derivative of all the instruments with respect to all the spine points, and we just store those in a matrix J. So let's go back. So here we have here we still have this iteration. So it's a Newton-Raphson. We evaluate instruments, we perform Jacobian, and then what we have to do, we have to inverse Jacobian. And this is what we do with the NumPy linear algebra toolset. We do inverse of Jacobian, and then we define an error. So the error here is defined as the minus Jacobian, and minus inverted Jacobian times the vector of the values. And then we define essentially next Ri, so the next set of our spine points, as being the previous set of spine points plus this called error, let's call it. And error basically expresses the difference between the two consecutive sets of the spine points. So of course, as this difference between two spine points or two iterations between the spine points, as this difference is small, then our optimization should stop. But this is how we define here. So we look at the we define the error essentially here to be maybe it's a little bit inconvenient that we are using the same notation for this error here and error here. This is basically this error here is the difference between two consecutive vectors of our spine points in two iterations, in one iteration from the previous step and the new step. And here the error is defined just as the norm of the difference between two sets of the spine points. And this is what we'll be printing here. So you see, it's a very simple for loop. For loop, while loop. Of course, the risk here is that if we don't have any convergence, this loop will be running infinitely, so it will never end. So sometimes it's a good idea to also count. You see, we have this index of number of iterations, and I'm using this index here to print the output, just to indicate how many iterations was needed to perform the calibration. But highly recommended would be that you also make some kind of limit on number of evaluations. So let's say if the number of evaluations is higher than 100 times or 50 times, then you should throw an error message saying that the calibration wasn't successful. Otherwise, if you don't have it, then essentially you can crash your Python. And imagine yourself, if you be a trader and code runs immediately and takes all the computational resources from your machine, that would not be very desired. So those kind of protections is good to introduce in your code. Here, of course, I didn't do it because a simple reason I want to be very transparent how this code should work and how to implement it. But this is not production code. Okay, so we have seen here. So once this Newton-Raphson is finished, the output will be a vector of spine points, and this will be the output of our metrics of our function yield curve, and this yield curve is here. So what we do next? So once we have yield curve, we will print this spine points on the screen, right? And what we can do, we can now define, we can look at the evaluation of swaps before we build the curve. So let's say the initial curve. So this curve is called initial because what I'm doing here, I'm just building a curve on the spine points. So we have these maturities from the market. And I also use R0, which is here. So this is R0 is this 1% interest rate. And then the second zero coupon bond or second curve, you can say yield curve, will be one I'm building based on the maturities. But here, these RIs are the spine points built or obtained from this calibration we have received. And once we have those two, what we can do, we can iterate over all the swaps we have in the portfolio, and we can calculate what is current PV of those swaps. And obviously, we don't expect that we have a PV of 0 if we take the initial one. So this is this is the initial one. Actually, it'd be nicer if we have a first initial one, and then we have our ultimate one. So here you see, I'm doing this for initial for each of those zero coupon bonds. For each swaps, I calculate based on initial yield curve. And the second set, I'm just doing for the calibrated yield curve using this RI spine points, which come from here. So let's run it. Okay, so you see it was super fast. Let's run it again. It's very fast. It's just a few milliseconds, even for this this computer. So you see here we only needed about 6 iterations to get 10 to minus 15. 7 we have 6, 7 iterations, we have about 10 to minus 17. The difference, let's say norm on the difference between the different collocation points, different spine points, the different iterations of our optimization routine, 10 to minus 17. The spine points that we obtained, those are the spine points. So those are RIs. We can also look at the swaps at the initial. So the initial yield, you see them really far away from par, being par. And then we do pricing of swaps using our yield curve, calibrated yield curve. You see that everything is 10 to minus 17. Here is actually even maybe lower than 0. This is 10 to minus 18. I think all of them that the machine precision level. So this is highly satisfactory. Everything works very well. Next step, of course, would be to improve the code. So you can see that, okay, swap definition is rather standard, but here we have done quite some numerical, let's say, brute force approach, especially in the calculation with Jacobian. You can see that here we calculate Jacobian simply by shocking our present values. So this is the part that we could improve. Whenever you see, especially in terms of, let's say, linear products, interest rate products, when those are really explicitly given in terms of zero coupon bonds, we can calculate those sensitivities, those derivatives analytically. Typically in a library, if you have a swap, that typically the swap doesn't really change. So sensitivity of your swap to zero coupon bonds to spine points, and also interpolation effect, those typically are done analytically so that we don't need to perform shocking. And here in this case, that would also benefit for us because then this extra evaluation, because we had to perform it 2 times, the evaluation for every iteration. So here, in this case, you can say we had 14 times evaluation while we could only have 7. On the other hand, if we shock here those spine points, this will also have impact on the accuracy. If we have no error essentially in a derivative calculation, that would also facilitate faster convergence. So maybe we could have, instead of 7 iterations, maybe we could have only 5. So those are the things that you could think of once you have you're working on a production environment where you really want to have it as fast as possible. Here you could see that this is sufficiently fast for, let's say, academic purposes. In next part, we'll be talking about hedging and delta sensitivity of your swaps to market instruments, then you will see that by changing interpolation, this will have actually significant impact on timing. And you will see it will be very clear from the experiment that interpolation routine is important, actually can really slow down your computation. And you, although things are maybe seem to be very analytic, let's say very simple to calculate, they can take quite some time if you really, if you have large number of instruments and you have quite, let's say, involved interpolation routine, those sensitivities and evaluations could be quite substantial. For yield curve, which is already built, we already have seen it how to construct it given a set of market instruments. Now is the time where we will dive into the concept of hedging and impact of different interpolation routines on hedging aspects. So we will discuss a few of the interpolation routines. We will talk about the speed and also what is the impact, whether the results, the hedging results, will make some sense or not. So we also, in this part, we will perform a Python experiment where we will define a swap and we will analyze what is the delta or the sensitivity of a swap to the market traded instruments. That kind of a nice experiment, and we will change different interpolation routines and see how this what kind of impact is of those interpolation choices. There are many different interpolation choices if we talk about yield curve construction. It could be linear and log rates, linear and discount factors, quadratic splines, cubic splines, B-splines. Many different choices are available. And I would like not to discuss all the details of all of them because the literature on the choices of interpolation is rather rich. And I would highly recommend to go into an article of Patrick Hagen and West on the methods for constructive yield curve. You will find a lot of details on different interpolation routines and what are their advantages, disadvantages. Hagen also discusses the hedging aspects and he gives quite some details how to even calibrate, not calibrate, but maybe how to implement those routines yourself. And also, we will be focusing more on smoothness conditions and the impact of the hedging creation. So whether the interpolation is local or global, and the impact of that on our results. So that will be from that part. I would like to give you still some flavor on two, let's say, the basic interpolation routines. The first one is the straightforward interpolation that just you can easily think of, where we have a spine points. So those are the discount factors on the spine points. And if we just interpolate simply linear interpolation on those zero coupon bonds, that's the let's say straightforward naive approach. Although maybe straightforward, but also problematic a bit, because if you, for example, use your model, your yield curve, to simulate of a whole white model or any short rate model, very likely you'll be dependent on instantaneous forward rate, which is basically the log of a zero coupon bond. And if you don't have smoothness in this kind of interpolation on, let's say, zero coupon bonds, then you have a problem, because then this means that the theta function, the term structure of your short rate, will have a very weird behavior, and could be that even if you are simulating zero coupon bonds using full white model, which by definition should give you yield curve back, exactly the one which is used as an input, that could not be the case. Yeah? So that could happen that your full white is not even able to calibrate to yield curve and return yield curve back. So that's a problem that you could have if you have this kind of interpolation, and because the interpolation here does not guarantee differentiability, so it's not differentiable, zero coupon bond. Another approach that we also have done in this code, we differentiated on a log discount factors, and that kind of improves, so some of the limitations of these interpolations are improved. This is kind of equivalent if we talk about linear interpolation between forward rates. So this is also, I always prefer this one than this one. But as you have seen already in the previous lecture, I also changed these interpolations to B-splines, for example. And I was kind of happy with those results. Everything, of course, depends also on your market data and also sometimes on the market conventions. What can happen also in the building of a yield curve is that you may have two different interpolations. The one interpolation for short end. So, for example, for instruments shorter than with expired maturities shorter than 1 year. Those are the cash instruments, maybe some forward rates. And you can have a different set of or different interpolation routine for far end. So this means for instruments like swaps, which are maturing later than 1 year. And so after 1 year, those are typically considered to be long end. The interpolation on both sides can vary. And also this has to do with the fact that if you are on a short end of the curve, on a long curve of the curve, you may have a different objectives. Yeah? So this is also, let's say, traders' perspective is important to take that into account once you build a curve. Okay, so what are the, let's say, the so-called localness of the interpolation methods? So if we have a change, so if we have a spine point, and we perform a kind of change or shock, you can say, or also maybe a delta, then we would like to choose the interpolation routine such that the impact of your shock of a spine point is as localized as possible. This would mean that we have this interval around this spine point in the time, and then we would like to have it as narrow as possible, so epsilon going to 0. To address that, you could think of course, linear interpolation, because linear interpolation only is considered to be local interpolation. Also, you may have a monotone piecewise cubic method. Splines, of course, are less attractive because those will be splines are defined or not only about neighboring points, but also further away. So it could be involving multiple points further, so different spine points than your spine point of interest. Another very important aspect is to choose interpolation that the localized hedge takes place, and this is what we'll be discussing in this numerical experiment. And already something else I mentioned, that if you have a 5-year swap and your global interpolation implies that you should hedge it with 30-year swap, that may not be the best choice. So that could be impacted by the interpolation routine. So if I talk about the global interpolation or local interpolation, this is related to the how, if you have a shock on the short end, or if you have a shock of the spine point, which instruments on the curve will be affected by that. If they are done in a neighbor of that spine point, that's called local shock or local surrounding local impact. If you have a global, this means that shock on the curve in one place would have also impact on instruments which are far away from that spine point. So this is the difference between the two. But it will be very clear in a minute once we'll be looking at Python experiment, and we'll be experimenting ourselves on the different interpolation routines and impact on hedges. In a hedging experiment, we'll be relying on a function we have developed earlier for calibration of a yield curve. I have made only some small adjustments. One of them is that the construction of instrument set is essentially now just a function. So here we have a built instruments, and then for given set of strikes or fixed rates and set of maturities, we can just construct a set of instruments, a vector of instruments, vector of swaps. Of course, those are right now is just we have a portfolio of swaps. If you like to include additional instruments, you will need to adjust this function too. Here we also have made extension. Before we had only linear interpolation. Now we also have a cubic and quadratic interpolation. So those are Python functions that you can just import from the interpolation library. Functionality is exactly the same. Input and output is the TI and RI are the locations and points for the spine points, and then the output is basically the alpha expression, which will basically interpolate between those points using particular choice of interpolation, whether it's a quadratic or cubic. Now, those interpolation choices, we can specify here when we have a method. So by changing this part, we will observe the impact on the Greeks, on the delta. Here is basically, essentially is the same what we have seen before. So we have number of par instruments and given maturities. This is up to 30 years. We build those instruments, we construct the curve, essentially given, so this yield curve function returns the spine points, and given those spine points, we can build a yield curve, which is P0t. And now what we do, so at this point, we have a curve which is calibrated to the markets. Now we would like to price a swap. Swap, I call it off-market swap. This means that this is not a market given, this is not a swap given to construct a yield curve, but this is just a swap you would like to price. For example, you are working in a bank and your client calls you to for a swap. He would like to buy a swap. Then this is, for example, a hypothetical swap that we consider. This swap has a maturity of 4 years, so it's a third argument from the back. We go to IR swap function. So if we go back, we see 1, 2, the third argument. Okay, so this is the fourth argument from the back is the beginning of the swap, and the third from the back is the end of the swap. So now we have 1, 2. This is second. This is third. So a client wishes to buy a swap, which will start here. T0 is the initial point, so from today, let's say, and maturity of a swap is 4 years from now. So obviously, this swap wasn't used in calibration building of a curve. But now we will use the curve to price the swap. So this is the first part, and we would like to also to hedge the swap. So we would like to see sensitivity of the swap to all the market instruments that are used to calibrate the curve. So essentially, we have a curve consisting of market instruments. Those are the market instruments. Now we have off-market swap, which is it's not specified are the building instrument for the curve. And we would like to see the sensitivity of a swap, this off-market swap, to all the market instruments we have here. So essentially, what we have to do, we have to differentiate derivative. We have to calculate derivative of the swap to the market instruments which were used in building of the curve. To achieve that, we need to recalibrate curve for every instrument, shocked instrument in the portfolio set. So for example, if we have right now 8 swaps, we need to shock each of those swaps and then rebuild the curve and check what is the impact on the rebuild curve on PV. So what we do here, we see here that we first shock each instrument of the curve. We rebuild the portfolio for shocked instrument, but this is we do it one by one. So for every instrument, we have to redo this experiment. So we rebuild the new instruments with the shocked fixed rate. Then what we do, we construct a yield curve. So again, we have to rebuild the curve as we did before. Now, for a shocked curve, we have to recompute again swap, which is here, which is off-market swap. And what we do next, we define delta, which is a derivative of our swap with respect to each market instrument. So this is what we see here. It's a delta I, is a swap, shock minus swap, and then we divide it by the shock size. And we have to, and now what we do next, we remove the shock size. So we do it for instrument by instrument. So for the first instrument, we shock it. The rest of the instruments stay exactly the same. Then we shock back basically the first instrument. We go to the second instrument. So we never shock all the instruments at once. We do it one by one. And then for each of those curves, we recompute the value of a swap. And then that will give us the derivative, the approximation of a delta, which is derivative of our off-market swap to each market instrument. With this delta, we can conclude how much instruments used in the build construction, the building of the curve we have to buy or sell in order to hedge our instrument that client required to buy. So let us run it. So you see that it's still rather fast, but we had to do it multiple times. So you see that this is the first run where we did only the building of the curve. So we had 9 iterations. And then for each of those instruments shocked, we have to rebuild the curve. So you see, here's the first curve, here's the second curve, and so on. And we did it 8 times. And here on the bottom, you can see a delta profile of our swap. So our swap was had maturity of 4 years. We had it here specified. So we look here, it's a 1, 2, 3, 4, 5. So we see from here that the delta for the derivative of our swap to the first market instrument is negative. It's also negative for the second instrument, market instrument. We have a positive delta for the third and fourth. This is kind of nice to see because you see that if we had this swap, essentially we could hedge it with instruments which are third and fourth. This is you see this. It's a significantly larger number than 0.03 in absolute sense. So it's a 1, 2, 3, and 4. This means that we had to hedge our 4-year swap with 3-year swap and a 5-year swap. This is the main contribution that we can see from this delta profile, which is here. And then we have to buy, or actually this is the opposite sign, we have to offset with the swap with a very short maturity. So it's 1 and 2 years. But most of the delta comes from the neighboring swaps on the curve, which actually makes sense. So if you have a 4-year swap and we have instruments on the curve 3 and 5 years, it feels natural that we will need to hedge it with 3 and 5 years. This is kind of interpolation on the curve that we have to do, which is very much in line with our expectation. We also have 0, 0, 0, 0. This means that we don't need to buy anything beyond 4 years. So it's 7 years is not, we don't have any sensitivity, 10 years, nothing, 20 and 30 years, 0 sensitivity to that market instruments. So this is also expected. This is what we wanted to see, that by changing that we don't need to buy 30-year swap in order to hedge our 4-year swap that we just bought it or we sold it to our client. Okay, so this is something with line with our expectation. In this experiment, we had linear interpolation. This means it's one of those local interpolations, however, may be problematic in terms of differentiations, etc. Of course, we differentiated on PIs. So so this is local representation of the local interpolation on the spine points. Okay, so now let us change the interpolation from linear interpolation. Let's do it a cubic interpolation. So what we have to do, just have to replace this name here with cubic, and let us run. So the first thing we noticed is that time-wise, it is much more expensive to calculate, to build even curve with a cubic type of interpolation. This is related that we, of course, first of all, we rely on a library, which is a Python library. So that's maybe implementation-wise is not the fastest, but also we have to quite some operations we have to perform in the construction of a Jacobian. So you see that this is really, we can see a huge difference in time needed for construction of each of those curves. And obviously this can be improved, but at the first sight, if we had everything else the same, it's clear that the cubic interpolation is much slower than what we had for linear. Of course, this is also much more advanced interpolation because it's not only taking neighboring points, but we had many points more taken into account in the construction of the yield. Okay, so now let's take a look at the results. We see again sensitivities. We had, as we had before, we have the most of the sensitivity, most of the delta is between the third and fifth year. So the one of the what we had also for linear interpolation. However, here you can see also that because of the cubic interpolation, we also have sensitivities to products much later than the expiry of our maturity of our swap. So for example, here we have sensitivity to, this would be 3 and 4, we have 7, here we have sensitivity of 7. We also see sensitivity 10 years and also 20 and 30 years. Maybe it's not huge number here. However, you can see that, for example, for 10 years, it is rather significant, the hedge. So if you can easily see that because of the different interpolation routine, we may actually have better properties of the curve, that the curve is smoother, but the cost is at this point is that we may have a hedging issue. So our hedging expenses may be larger, especially maybe it's also counterintuitive for a trader to maybe not desired to hedge short-term swap with a long-term swap. This effect maybe is not so relevant if we are talking about a large portfolio involving multiple swaps that will be covering essentially all the, let's say, grid points. But for a single swap that we just considered, I would tend to say that this type of interpolation is not really desired. Here we could also try with a quadratic interpolation or maybe others. I will leave it to you as this will be one of the homeworks to check it. But for here was just to illustrate that impact of the interpolation on hedging can be significant and should not be neglected. So this is, I would say, the most important takeaway from this part of the lecture.